In this video, we're going to continue to look at other reactions of carboxylic acid derivatives, specifically esters and amides. Let's think about the preparation and reactions of esters. So if we start out with a carboxylic acid, this can be treated with an alcohol in the presence of H+, and this is a Fischer esterification to give an ester. This can also be done by an SN2 type of reaction, where an acid is first treated with sodium hydroxide to pull off this proton, and then this acts as the nucleophile, treated with an alkyl halide to give an ester. Alternatively, an acid chloride or acid bromide can be treated with an alcohol. It will undergo nucleophilic acyl substitution to give an ester. This can also be done with an anhydride. So there are other ways that esters can be made. These are some of the common ways. So what about reactions? Keep in mind, esters cannot be converted into acid halides or anhydrides by nucleophilic acyl substitution. They could react with an amine to give an amide, but that's not really common. They can be hydrolyzed under acidic conditions or basic conditions to give a carboxylic acid. They can be reduced using lithium aluminum hydride followed by water, and they would be reduced to a primary alcohol and your other alcohol as well. They can be reduced using diisobutyl aluminum hydride, and this is usually carried out at -78 degrees, and this one will stop at the aldehyde and does not get reduced all the way down to the alcohol. So you will get an alcohol corresponding to this side, but this is reduced to an aldehyde and then it stops there. And finally, one other reaction we've seen is treatment with a Grignard reagent. So step 1, step 2, H3O+, and this will give us an alcohol resulting from the addition of two equivalents of Grignard. So the first equivalent does nucleophilic acyl substitution, where this is kicked out, giving us a ketone, and then a second equivalent will add to the ketone, giving us this alcohol. So these are some of the most common ways of making esters and some of the important reactions of esters as well. Another important thing about esters is that if you have a molecule with a carboxylic acid and an alcohol in the same molecule, and this is exposed to acidic conditions, it can undergo an intramolecular esterification to give a cyclic ester. Now, a cyclic ester is called a lactone. So an intramolecular esterification reaction is called a lactonization. Typically, these are characterized by the size, and so if we focus on the carbonyl carbon, the next position is alpha and then beta, gamma, delta. So this is a delta lactone. If a hydroxy acid can form a 5 or 6-membered ring, then the lactonization will be spontaneous with just a little bit of acid. If you're trying to make a smaller ring, 3, 4, or a bigger ring, 7, 8, or bigger, then it's not as easy. Now, there are many important natural products that have very large lactones. This is erythromycin A, and we can see we have an ester, so this is a ring, so this is a lactone. Now, because many important natural products have really large lactones, these are called macrolactones. there have been special methods developed to make these macrolactones. And so there are methods for macrolactonization. For a long time, there were a number of Japanese groups that developed methods that could be used to make lactones in natural products. And so there is the Mitsunobu macrolactonization, Yamaguchi macrolactonization, Mukiyama macrolactonization, and this is just a small sample. So down here, we have an example. So here is a carboxylic acid and here is an alcohol, and these are the two that need to be made into an ester. But rather than just trying to close this up, Corey and co-workers used a special macrolactonization method where the acid was converted to this special thioester, and then this can undergo reaction to form this macrolactone. Now this is converted in several additional steps to give this compound, erythronolide B, which has been used as an antibiotic for decades. Here's another important natural product called amphotericin. This is used as an antifungal medication. Nicolau and co-workers reported the total synthesis of this precursor called amphoteronolide, and it is very similar to the final product, except that it doesn't have this sugar attached here. But they made these two big pieces, and then here is a carboxylic acid and an alcohol, and this used a macrolactonization method to form this ester, where this is the bond, the new bond that was made. And also over here, this aldehyde reacted with this group here. This reaction is called the Horner-Wadsworth-Emmons reaction, and it's kind of a cousin of the Wittig reaction. This carbonyl is retained in the product, and then this carbon is now double bonded to this carbon in the product here. So technically, because this was done first, it wasn't a macrolactonization, it was just an esterification reaction because this was done first before the Horner-Wadsworth-Emmons reaction. But just another interesting one. And finally, let's think about preparation and reactions of amides. If we focus on preparation by nucleophilic acyl substitution, then we know that an acid halide can react with an amine to form an amide. An anhydride can also be used to form an amide, and although it is less common, an ester can be used to make an amide. Now, what kinds of reactions will amides undergo? If this is a primary amide, this can be treated with thionyl chloride or phosphorus pentoxide or phosphorus oxychloride, and that will give a nitrile. But if we focus on nucleophilic acyl substitution reactions, this can be hydrolyzed. Well, if this is treated with water, we get no reaction. And that's a really good thing, and we'll come back to that in a second. So if it is treated with water under acidic conditions, then you will get hydrolysis so that we get an acid, or under basic conditions, this can also be hydrolyzed to give technically the carboxylate. Now, why is this important? So amides are unstable under acidic conditions or basic conditions, but they are not reactive with water when the solution is neutral. This is really important because what it means is that at physiological pH, amides are stable. Well, an amide linkage is when it's in a protein, it's referred to as a peptide linkage. So if peptides would react with water, then we would have no proteins, right? Because everything would exist as amino acids, not as proteins, if they could be hydrolyzed. In the body, under acidic conditions, they can be hydrolyzed. So this is why your stomach has acid, so that proteins in your burger can be broken down, hydrolyzed into acids. I just realized I went a little crazy with lone pairs because there's only supposed to be one lone pair here. Sorry about that. There's one other reaction that I didn't leave myself room for, and that is reduction using lithium aluminum hydride followed by water. And in this case, what we get is an amine. So the hydride acts as a nucleophile, shares electrons with the carbon, pushing these electrons up, and that gives us an intermediate that looks like this, where this oxygen is going to be complexed to an aluminum species, and then this nitrogen can share electrons with the carbon, pushing away oxygen to bond with the aluminum species. And that would give this, with a positive charge on the nitrogen, this is called an iminium ion. And then another equivalent of hydride can add here, pushing electrons back on to the nitrogen, giving this amine. So two hydrogens were added to the carbon, and both of those hydrogens came in the form of hydride ions. So amides can be reduced to amines. So just a little bit more to consider in terms of amides. Just a moment ago, we saw that a cyclic ester is called a lactone. Well, we can also have a cyclic amide, and this is called a lactam. Once again, focusing on this carbon, alpha, beta, gamma, delta. So this is a delta lactam, for example. Here is an example of a beta lactam antibiotic. So penicillins, for example. This is the cyclic amide, so this is the lactam, and this is the alpha position beta. Beta is connected to the nitrogen, so this is a beta lactam. Notice we also have an amide over here. So like most amides, this is not very reactive. Beta lactam, it's not reactive because it's an amide, but this is highly strained. A four-membered ring is going to be highly strained. So a beta lactam is reactive. So this is important because many of these beta lactam antibiotics can react with an enzyme that is responsible for building cell walls, and this can react here, push up these electrons come back down, open up the ring, and so it will give you something that looks like this. And up here we still have our regular amide. But notice this enzyme is now covalently bonded to this molecule. And so the active site of the enzyme is no longer active. So the enzyme is effectively dead, can't build the cell wall, which means the bacteria can be killed. So with a number of beta-lactam antibiotics, these groups can be varied, but more commonly the R group can be varied, and that's going to affect properties such as adsorption or distribution, how it's metabolized, how it's excreted. So a lot of antibiotics with this general structure have been developed. Now, as we're thinking about penicillins and other beta-lactam antibiotics, We all know that Alexander Fleming was given credit for discovering penicillin as a very useful antibiotic. It's a very interesting story because his discovery was somewhat accidental. He kept a very messy lab, went on vacation, came back, and found that something was killing the bacteria that were left on the plates that he didn't clean off. And so, yes, he discovered the particular compounds, but it was Flory and Chain from Oxford, as well as Heatley from the USDA, who developed fermentation methods to be able to make larger quantities of penicillin so that they could be used as antibiotics. So this was happening during World War II, where antibiotics were critical. And until there were methods to be able to make penicillins in very large quantities, the antibiotics were so critical that they were actually isolated from urine to be able to reuse the compounds. Also of note is Dorothy Crowfoot Hodgkin, who solved the X-ray crystal structure for penicillin, and determining that structure was also very important to be able to make large quantities of penicillins, and also to be able to make variations of the penicillins that could be effective against different types of bacteria. So that takes care of our look at synthetic applications of different types of nucleophilic acyl substitution reactions, as well as other reactions of carboxylic acid derivatives.